Hello students, this is Professor Chalai, and in this video we're going to look at thermochemical equations. As always, you can follow along with our Chapter 5 workbook. By the end of this video, you should be able to write thermochemical equations and solve other problems involving thermochemical equations. Let's get started. So you might be asking, well, what is a thermochemical equation? A thermochemical equation is simply a balanced chemical equation. Let's write that again. Equation with an associated delta H value. And so I'm going to write an example of that using the problem stated in question 18. So in question 18, it asks us to write the balanced chemical equation for this reaction, HCl with NaOH to form NaCl and water, for 1 mole of HCl. So we have HCl plus NaOH aqueous going to give NaCl aqueous plus water liquid. And as stated in this question, it's for 1 mole of HCl, and so when we balance this equation, we need to make sure that we have 1 mole of HCl. Sometimes to balance it with what they ask, for example, in this one it's 1 mole of HCl, you will have to end up using fractional terms to balance. For example, this one was balanced for 1 mole of butane, so we actually had to use 13/2 moles of oxygen. That can happen in thermochemical equations. So here's the example of another thermochemical equation. So we have the balanced chemical equation with the delta H value written right next to it. So in the example that I've shown, we'll have the balanced chemical equation and the delta H value for this equation written right next to it. Usually that delta H will have a value in kilojoules. So in question 1, they're asking us to complete this thermochemical equation. We have the balancing part right. Now we just need to figure out what the value for delta H here will be. So let's look at it. So here it tells us that we have 0.05 moles of HCl, 0.05 moles of NaOH, and 0.05 moles of product forming. Now typically when they give you the values of multiple reactants or products, one of those might be the limiting reactants, and that's the one you need to use to solve the problem. In this question though, they're all equal and the number of moles are all equal in these cases. 1 mole of HCl, 1 mole of NaOH to 1 mole of NaCl, and the number of moles that we started with of our reactants are the same. So we don't need to figure out which one's the limiting reactant. They're both available in the exact appropriate amounts. So the delta H value is written for this equation, which is for 1 mole of HCl or 1 mole of NaOH or 1 mole of NaCl. So if this is the amount of heat produced, 2.9 kilojoules, then the delta H for the reaction will be that 2.9 kilojoules for 1 mole, should be written for 1 mole of HCl. But in fact, what we have is 0.0500 moles of HCl. But it should be written for 1 mole of HCl. There we go. So if we solve for this, then we get a delta H value of 58 kilojoules, but the heat is produced, so this value should be negative, because if heat is produced, it's an exothermic reaction, the delta H value should be negative. So this delta H for number 1 should be minus 58 kilojoules. If we had instead chosen NaCl as our limiting reactant, then this would have been negative 2.9 kilojoules, that's the heat produced, divided by 0.0500 moles of NaOH, sorry. But this reaction has 1 mole of NaOH. So we multiply by 1 mole NaOH, which will give us the same value, minus 58 kilojoules. So what I just did was found the amount of heat needed for 1 mole of HCl or 1 mole of NaOH. We could have done the same for 1 mole of NaCl or 1 mole of water. usually they will give you the amount of heat produced for whatever amount of moles they used in the actual reaction, and you just need to find it for one mole. The number of moles of your reactants or products is given by the balance equation. So if you were to balance this equation differently, then the delta H value would be different. All right, try numbers 19, 20, 21, and 22 by yourself. Remember that the balanced chemical equation will have a delta H value associated with it, usually in kilojoules, and it's for example here, 1 mole of sucrose, or 8 moles of potassium chlorate, or 12 moles of carbon dioxide, and so on. So try to find the delta H for number 19. Note that for number 19, you have 2.67 grams of sucrose and 7.19 grams of potassium. One of those is probably the limiting reactant. That's the one you need to use to balance to find the delta H value. Okay, let's go over number 19 now. As I mentioned, we have two different reactants, two different amounts. One of them is probably a limiting reactant. So let's figure out which one is the limiting reactant and then use that to find the delta H. So when we find limiting reactants, we usually figure out which one forms the lesser amount of product. In this case, we have three different products. I'll just pick the carbon dioxide as the product that I'm interested in. It doesn't really matter which one. And let's start with the sucrose. So for the sucrose, the number of moles of product, so the number of moles of CO2 that we form will be, we first find the number of moles of sucrose, which is the mass of sucrose, divided by the molar mass of sucrose, which we calculate to be 343.3 grams per mole of sucrose. And then we use mole ratios. For every 1 mole of sucrose, there are 12 moles of carbon dioxide, so 12 moles of CO2 for 1 mole of sucrose. And so this will give us 0.0933 moles of CO2. All right, what happens if we start with potassium chlorate? Our number of moles of product that we end up with is going to be, we start with 7.19 grams of potassium chlorate. The molar mass is 122.55 grams of potassium chlorate per moles of potassium chlorate. And then we convert moles of potassium chlorate to moles of carbon dioxide. So for every 8 moles of potassium chlorate, we get 12 moles of CO2, which means that the number of moles of product that we form is 0.0880 moles of CO2. Looking at these two amounts, we can easily recognize that that is the smaller amount of product, which means potassium chlorate is our limiting reactant. What this means is that this amount of energy in the question that was produced came from burning all of the potassium chlorate, and there was excess sucrose left over, which we're not really interested in. Okay, so we know that potassium chlorate was our limiting reactant, and we know that the amount of product that we formed for it was carbon dioxide, and we formed 0.0880 moles of carbon dioxide. So since this is the amount, we know the amount of one of our reactants or products, let's find our delta H value using that. So our delta H value would be for 12 moles of carbon dioxide. So our delta H for 12 moles of carbon dioxide, the amount of energy that we got was 43.7 kilojoules, right? And this was for 0.0880 moles of CO2 because that's what we got from our limiting reactant. But we need to write this for 12 moles of carbon dioxide, so let's write it multiplied by 12 moles of CO2. And so the delta H value that we end up with is going to be negative 5960 kilojoules, negative because heat was produced, so it's exothermic. So to complete this delta H reaction, we get minus 5960 kilojoules. So let's highlight this entire thing as the thermochemical equation. Okay, so what did I do? First, I found a limiting reactant, and we find that the amount of product that will produce, we just used carbon dioxide, we could have used any of the three products, was 0.0880 moles of carbon dioxide. But the delta H needs to be written for the equation, which means it should be written for either 1 mole of sucrose or 8 moles of potassium chloride or 12 moles of carbon dioxide. So we should, since we know the amount of carbon dioxide we have, let's roll with that. We got 43.7 kilojoules of heat for 0.088 moles of carbon dioxide, but we need it for 12 moles of carbon dioxide, so we multiply it by 12, and that's the amount of heat we get. All right, try numbers 20, 21, 22. If you haven't already, pause the video, and then when you unpause, I'll go it over with you. Okay, let's look at number 20. In number 20, they already give us the thermochemical equation with the delta H value, which means this delta H is for 1 mole of propane or 5 moles of oxygen or 3 moles of carbon dioxide and so forth. They tell us that, I like to write that. So the delta H will be minus 2044 kilojoules for propane is the substance that we're interested in. So it's for 1 mole of propane. So if we figure out how many moles of propane that we have, then we can figure out how many total amount of heat that we actually produced in kilojoules. So to figure out how much moles of propane that we have, let's do that. So moles of propane. We start with the mass, 13.2 kilograms, but we need to convert to grams before we can convert the number of moles. So let's do that. And then we will divide by the molar mass. In this case, they already give it to us, so we don't have to calculate it. Grams per mole. And so that will give us 299 moles of propane. So if we multiply this by 299 moles of propane, we will get an answer of minus 611,000 kilojoules. So this is the amount of energy that we produced when we burned 299 moles of propane, which is what we got from the mass. Just what I did was I took the delta H value, and since this delta H is for this entire equation, but we're only interested in it for propane, I express it in terms of the number of moles of that substance, propane. Okay, let's look at number 21. If you haven't already, pause the video here, solve number 21, and then when you unpause, I'll go it over with you. Okay, in number 21, we'll also have our balanced thermochemical equation, and the delta H is given. Here, we're asked to calculate the heat associated with the reaction of ammonia. So let's rewrite the delta H in terms of ammonia. So this delta H is for 4 moles of ammonia. So it's minus 906 kilojoules for 4 moles of ammonia. So to figure out how much energy we get from this reaction for this amount of ammonia, we need to figure out how many moles of ammonia that is. So the moles of ammonia, we start with 155 grams. We divide by the molar mass of ammonia, which I assume we all know how to calculate by now. And the molar mass of ammonia is 17.03 grams per mole, which gives us 9.10 moles. So when we burn 9.10 moles of ammonia, according to this equation, we should get, let's see, 906 divided by 4 multiplied by 9.10, I get minus 2060 kilojoules to 3 sig figs. All right, let's look at number 22 now. They'll also give us the balanced thermochemical equation. So this value is for 1 mole of C4H10 or 13 over 2 moles of oxygen or 4 moles of carbon dioxide or 5 moles of hydrogen. But let's look at the question and see what they're asking. They ask for the mass of butane to produce this amount of heat. So we should express, well, let's write the expression in terms of butane. So this delta H minus 2658 kilojoules is for 1 mole of butane. And when we multiply that by the number of moles of butane that we actually burn, which we don't know yet, we will get this amount of heat. So we'll get 1.5 by 10 to the third kilojoules of heat. So let's figure out how much moles of butane we probably burn. So X moles of butane should then be equal to 1.5 times 10 to the third kilojoules of total heat. And then we divide both sides by this. So we divide by minus 2658 kilojoules per 1 mole of butane. C4H10, there we go. And so our answer will be in moles of butane. And we can get rid of the negative sign because we know heat is produced. We can't have negative number of moles. Okay, so according to this, we should get 0.56 moles of butane, C4H10. So let's put a circle around that because that'll be important later on. So this is the amount of moles of butane we need to burn to get this amount of heat. What amount of that butane is that in grams? Well, to convert moles to grams, all we need to do is multiply by the molar mass. So 0.56 moles of butane times the molar mass of butane, which is 58.12 grams per mole. I'm assuming we all know how to find molar masses easily now. That will give us the 2 sig figs 33 grams of butane. So that's one part of the answer. That's the mass of butane in grams. The second part of the question is, what mass of CO2 is produced? Well, to figure that out, let's use mole ratios. We know the number of moles of butane that we use. So we use 0.56 moles of butane. How does that relate to the moles of CO2? For every 1 mole of butane, we produce 4 moles of CO2. So for every 1 mole of butane, we produce 4 moles of CO2, which means that this gives us 2.2 moles of CO2. The question then asks for mass of CO2. So if we have 2.2 moles of CO2, we can multiply by the molar mass, which is 44.01 grams per mole. Plug that into our calculator, and we will get 96.8 to 2 sig figs, 97 grams of CO2. So that's the answer to our question. We use up 33 grams of butane, and we produce 97 grams of CO2. Alright, so this brings us to the end of our video on thermochemical equations. Just know that a thermochemical equation has a balanced chemical equation. Let's look at any example. Let's look at the example we just looked at. A thermochemical equation is a balanced chemical equation with an associated delta H value. The chemical equation can have fractional numbers to balance it. That's okay. And this delta H value is for the equation as written. So it's going to be for example, 1 mole of butane or 13.2 moles of oxygen and so on. And so we could use that with our knowledge from stoichiometry to figure out how much moles of reactants are used up or how many moles or masses of products are produced in our thermochemical equation. Or we could use it to figure out how much heat is produced when we burn up a certain number of moles of reactants. There's lots of things we can do with thermochemical equation. It relates the number of moles to the heat produced in thermochemical reactions. All right, that brings us to the end of this. In our next video, we're going to talk about measuring the enthalpy changes in various reactions. I'll see you then. Bye.